Let's take a look at the definition of the derivative by looking at an animation. So our goal here today is to find the slope of the tangent line that could be drawn right here at point P. So let's draw that tangent segment and just show you what it looks like. Okay, and we're already being shown what the tangent slope is, but let's see how we could derive that if we were trying to do this by hand. Okay, so here's our tangent line. Now, from classes that we've taken before this year, you know that you can find slope of a line by choosing 2 points on the line and find the slope. So by looking at the change in y over the change in x. Well, let's see if we can get another point on our curve. So we can do that. So let's move over h units from x. Right here, we went from x to x plus h. So in green, we're going to plot a new point, and we're going to label it Q. Okay, now let's connect those 2 points with a secant line. Okay, so what we want to do is find the slope of this green line in order to approximate the slope of the tangent line. Well, as you can see, they are both positive slopes, but they're not super close. They're not lining up as well as we would like. So you could find the slope of PQ, and you could say it's an approximation of the tangent line slope, but it wouldn't be a good approximation because Q is so far away from P. So our next question is to think, how could we get Q closer to P? Well, remember we went over h units. So how about if we let h approach 0? Let's look and see how that would look. As h approaches 0, look what happens to that secant line. Okay, and I'm going to stop the animation and just do this manually one time to show you something. So here's point P, point Q. As Q gets closer to point P, the slope of the secant line becomes closer and closer to the slope of the tangent line. So I'm going to manually change h now. Notice I'm letting h get closer and closer and closer and closer to 0. Once we get almost to 0, now we can't actually equal 0 because remember when you're finding slope, if the change in x's cannot be 0 because the fraction's result would be undefined. So let's back it up again and let's think about how this limit statement comes about. So what you think about is point P is the ordered pair x f of x. Point Q is the ordered pair x plus h, comma, f of x plus h. Well, if I find the slope using points P and Q, it's going to look like this: f of x plus h minus f of x, which is the change of the y values, divided by x plus h minus x, and so we're left with just h. So this part right here, not including the limit, is what we would call the slope of the secant line. But we don't want the slope of the secant line. We're using it to help us find the slope of the tangent line, but we don't really want just the secant line slope. We want the tangent line slope. So what we do is we say, well, this is what we call the derivative, and the slope of the tangent line is the limit as h approaches 0 of this difference quotient, okay, which is really just the slope of the secant right here. So once we take the limit as h approaches 0, it now becomes the slope of the tangent line. And let me just show you that one more time. So as h approaches 0, the secant line approaches the tangent line. And on here, I can actually have them line up. But keep in mind when you're evaluating that limit, h is getting infinitely close to 0 without actually ever equaling 0, because otherwise we'd have an undefined expression here. Okay, so I just wanted you to see this. This is what I was trying to show in the help session the other day, and I couldn't share my screen for some reason. So I'd like for you to understand why we do evaluate the limit statement like this, and this is called the definition of the derivative. And there's other forms of this, but this gives you a good idea of how we can get started with this.